In this lecture, we're seeing how in a real optical system, we're not dealing with only paraxial rays, but a much larger potential bundle of rays. We're looking at aperture stops and field stops, which can be used to control those rays, and the entrance and exit pupils that are calculated from the physical stops. We're going to look at F number and the effect of F number on the image and the depth of field. We're also going to be looking at aberrations. These are aberrations of perfect spherical lenses. So we'll look first of all at spherical aberration, then coma, astigmatism, also field curvature and distortion, and ways that we can minimize them. Finally, we'll look at chromatic aberrations and how we can minimize those. Up to now, we've been concerned with the path that rays take in optical system, particularly when they form an image, and we've been looking at the size and the position of the image that's formed. But in this lecture, we're going to be considering something else. We're going to look at the field of view, so that is how much of the object and other space around the object we can see in the image, and also the brightness and luminance of the final image. The physical things in our optical system that can affect the field of view and the brightness and the luminance are the way that the bundle of rays traveling through the optical system is limited. And the thing that limits the bundle of rays are the rims of the optics, which are considered to be stops or even additional stops that are placed into the optical system. An optical system really only collects a fraction of the energy that is emitted by the source. So any element that determines the amount of light reaching the image is known as the aperture stop. In this case, the amount of light is indicated by the size of the bundle. And you can see in this system, the size of the bundle is determined by this diaphragm here. And we will call this the aperture stop. You can see that a ray can even enter from quite an oblique angle, and it will still go through the imaging system. On the other hand, there is an element that limits the size or the angular width of the object that can be imaged, and that's called the field stop. In something like a camera, it's the edge of the CCD itself that indicates the edge of the image plane and is the field stop. If this aperture stop was removed, then the functional aperture stop is actually going to be the rim of this lens, because that is what is determining now the amount of light reaching the image. So as we've seen, the aperture stop limits the size of the bundles of rays that can get through to the focal plane, and therefore controls the amount of light and the brightness in the image. And if there are no additional diaphragms inserted into the imaging system, the rim of the lens forms the aperture stop. So on the other hand, the field stop controls the angle at which the incident light rays can get through. And it's used to prevent off-axis rays coming in at a very large oblique angle from contributing to the image. It's what decides is going to be the maximum size of the image and controls the field of view. Another useful concept that we can use to determine whether or not a certain ray will go through the whole optical system is the pupil. If we look at the aperture stop here through the front of the lens or even through the back, the aperture stop may appear to have a different size and location from where it actually physically is located and its physical size. Why is that? So our stops don't actually look the right size or in the right position. They're somewhere else. Why is that? Because we're looking through lenses. If we were to take some kind of optical system like this and we place a stop in between, if I view from the object side, I see the entrance pupil. If I view from the image side, what I see is the exit pupil. So the stop, when imaged from the object side, is the entrance pupil, and when imaged on the image side is the exit pupil. So in this problem, you're going to find the position and size of the entrance pupil. That is the side that light enters from, which is the object side. So we're going to view from here. So here is our stop. We are going to find out the size of the entrance pupil. We need to image in reverse now because we're viewing from the object side. So this will be our object distance here, O, and because the stop is a real object, then this is going to be O is going to be a positive number. And we use the focal length of F is 60 mil, and we can work out where it is located, I. To determine the size, then of course we need to know the magnification, which is going to be minus I over O. Now let's consider the brightness of an image. It's going to be related to two things. One is going to be the amount of energy that's gathered by the lens or the optical system. And that's going to be proportional to the area of the lens, or in particular to the area of the entrance pupil. Now the area of the entrance pupil is going to be proportional to the diameter of the entrance pupil squared. The other factor that's going to affect the brightness of the image is the size of the image, because the brightness is related to the energy per unit area. So if we change the image area, then that's going to change its brightness. So the image area is going to be related to the focal length of the lens squared. So of course, if we were to confine the image to a really, really small area, then it would be very, very bright. So we now have the flux density at the image plane is going to vary as d over f all squared. So d over f is known as the relative aperture, and if we invert that, f over d, we have something called the focal ratio, or the f number. We'll have a look at a simple example where we calculate the f number, which is equal to the effective focal length divided by the diameter of the entrance pupil. In this case, we have a single lens system, so the effective focal length is simply the focal length of that lens. We also have no additional apertures, and the only aperture stop in this system is the rim of the lens itself. So in that case, the entrance aperture diameter is A. So our f number is f on A. So this is a slightly more complicated problem. First of all, we need to find the effective focal length. We've got a 2-lens system, so you can look up your notes from last week. How do we find the effective focal length in a 2-lens system? The next thing we need to know is the diameter of the entrance pupil. Now, the entrance pupil is something that you figured out in problem 1. And so that gives us an F number of the effective focal length over the diameter of the entrance pupil. Part C, we're going to find the location of the principal plane, so you'll calculate H1 and H2. Then, for some ray tracing and visualization practice, you need to plot an incoming 60mm diameter axial ray pencil. So across here we have the dimensions of 60mm, and this pencil of rays is traveling parallel to the optical axis. What happens when it hits H1? What happens when it hits H2? And where is it focused? And most importantly, are any rays excluded from the optical system? So the F number determines the rays that can get through the system. In changing the number of rays that can get through the system, we're going to affect the brightness of the image. We'll also affect the sharpness of the image, because as we shut down the aperture and increase the F number, then we are going to restrict the rays to those that are closer to paraxial, and that means we're going to see fewer aberrations. We're also going to see that F number changes a property of the imaging system called depth of field. There's a related one called depth of focus. In the photographs below, if we set F number to be something, say 2.7, then you will have objects in the object plane that are sharply focused in the image plane, but those objects that are somewhat distant from the object plane are going to be blurry and out of focus. Now, we do something like change the F number to 8, and again, we find that the objects are still sharply focused on the image, but as you move away from the object plane, things do not seem as defocused on the image plane. Okay, so depth of field comes about, it's purely geometrical, when we have a system with, say, a lens and an image plane that is a fixed distance I. Now we know if we have only one I, then there is only one possible O distance where you can place your object and have the rays that will nicely focus and converge onto the image plane I. If we change the distance of our object, say we move it a little bit closer to the lens, then we know that those rays will converge slightly behind our image plane. And of course, if we move the object, further away from the lens, then the rays will converge closer to the lens here. Okay, so if we look at the image plane from front on, we'd see, a point corresponding to the point object, that's a distance O from the lens, and then we would see a sort of a circle instead of a point that comes from, it's got this diameter here, and it comes from the objects that are somewhat displaced from our object plane O. Okay, so the idea of depth of field comes about because we can't see the difference between a point object and a slightly larger circle. That might be because we are looking at it with our eyes and our eyes don't have perfect resolution. It might be because we're using an image sensor such as a CCD, and that's got a certain pixel size. So that means that whether the light arrives in the form of a point or in the form of a patch like that, until that blurry circular patch is larger than the pixel, we can still tolerate it and it won't reduce the quality of the image that we detect. So the size of that circular patch depends on the system. If the imaging system is our eyes and we're viewing it at our near point of 25 centimeters, then we can, for example, tolerate a point being imaged as a blurry patch with a diameter of 0.1 mils. So the depth of field is the range of distances over which the object can be moved and still be seen as sharp, because the circle patch, known as the circle of confusion, is smaller than our tolerance. So it's quite straightforward for a simple single lens system to calculate the depth of field. What we need to know is the diameter of the entrance aperture, and of course that's quite important because that determines the angle at which the light rays are arriving at the image plane. A larger angle means that we're going to see a larger blurry spot. We need to know the diameter of our circle of confusion that we can live with, the magnification, or if you don't have that, you can use I/O, and we need to know the F number and the object distance. So what these expressions give you is, we already know O and I for perfect focusing. Now, if we move a distance d1 in front of the object, then we could say that that's the distance where we've got a small blur that we can still deal with. And then we can move a distance d2 behind. In general, d1 is not the same as d2, and we'll still get a blur, but a satisfactorily small blur on our imaging plane. So the total depth of field is given by d1 plus d2. In these expressions, if we use the plus sign in the denominator, that's going to give us d1. The minus sign is going to give us d2. Another approximate expression that you'll find, there are different expressions, of course, depending what parameters you've got with you. You just pick which one's convenient. 2 times the F number times circle of confusion by object distance squared all over focal length squared. So the concept of depth of focus is kind of the image space equivalent of the depth of field. We have the situation now where we have an object and a lens distance that is fixed O. We know that at a distance I away, we will have sharp imaging of that object point in the image plane. So depth of focus is answering the question, how far can I move my image plane and not discern a decrease in the quality of the imaging of my point objects when they'll still look like point images. So the same factors determine the depth of focus as determine the depth of field. It's just got a slightly different dependence. Important factors are the focal length, the image distance, and the size of the circle of confusion, of course, and the F number. And of course, the easiest way to control the F number is to change the diameter of the aperture. So in this problem, I've got you looking at a mobile phone camera. It's got a certain focal length, it's got an entrance pupil diameter, and we've also got the width of the pixels. So each of those pixels is going to define the size of the circle of confusion that you can have. So first question is find the F number, and the second question is find the depth of field. You can find depth of field in front and the depth of field behind for an object that has O is equal to 2 meters from the camera. Now, our paraxial approximation doesn't, of course, actually apply to real lenses and mirrors. So as soon as we abandon that approximation of, sine theta is roughly equal to tan theta is roughly equal to theta, the whole geometrical optics just doesn't quite work and actually becomes really, really technical. However, the technicalities are very important. So we're going to have a look at some of them now. So it turns out that obtaining a good image is not so simple. Various things can happen to distort our image. So while we expect, something to have straight lines in our object, they might be imaged as curved lines. We might find that objects that are supposed to be points are imaged as blurry patches. And furthermore, we might experience a situation where we have, for example, a white spot, but we have the different colors imaged in different positions. So all of these are examples of aberrations, and we're going to see precisely what causes them and also what we can do to try and fix them. So we know that our Gaussian theory is really no more than a good approximation. So exact ray tracing would certainly reveal inconsistencies with our paraxial description. So departures from the conditions of Gaussian optics are known as aberrations. There are two types, chromatic aberrations and monochromatic aberrations. The monochromatic aberrations come about because we're using the paraxial ray approximation, and yet in any real imaging system, we have to accept light rays with angles greater than 0 degrees. So the paraxial ray approximation falls over. So there are 7 main aberrations. The monochromatic ones fall into 2 subgroupings. These first 3 affect the clarity of the image. They make it blurry. The following 2, field curvature and distortion, deform the image. Finally, we have the chromatic aberrations, which are related not to the paraxial ray approximation, but to our assumption that the refractive index is not a function of wavelength, it's a constant. Spherical aberration. It causes the image spot to blur. How does that happen? Spherical aberration can be thought of as the lens having a focal length that depends on its diameter. Rays that enter the optical system near to the optical axis will be focused at the paraxial image point or close to it. As the ray height increases, then the position at which they focus moves further and further away from the original paraxial focus. The distance from the marginal ray focus to the paraxial focus is known as the longitudinal spherical aberration. And the distance from the optical axis at the image plane, well, up to the defocused marginal ray, is called the lateral spherical aberration. There are expressions that you can find for both of these. You are free to look them up and use them as you will. Now, the amount of spherical aberration depends on parameters that describe just how much the rays are refracted. So the amount that the rays are refracted depends on the object and image distance, which tells you the angle at which the rays come into the lens. The radius of curvature, which also defines that angle, and the refractive index, which tells you how much refraction takes place. Now, these things may or may not be easy enough to change. Certainly the refractive index is probably one of the hardest things to change. So, what can we change? It turns out, practically at least, the most important thing that we can do is we can change the diameter of the pencil of rays that arrive on the lens. If we illustrate a single lens system down here with an object on axis a distance infinity away, then we can talk about the diameter or the radius of this ray pencil. We can also talk about the, another way to talk about it is the height. So we can talk about the height of that ray, the most marginal ray that gets through the system, and we can control the height of the maximum height of a ray that gets into the system using an aperture stop. So in this case, I have modeled the spherical aberration effects on a biconvex lens with a focal length of 5 centimeters and a refractive index of 1.52. So the x-axis indicates the radius of the aperture stop, which of course is the height, the maximum height of a ray that can get into the system. When the aperture stop is closed right down, and it means that only rays traveling along the axis can go through, then the effective focal length is 5 centimeters as predicted and as designed. However, as we get a larger and larger aperture opening, so we allow rays with a greater and greater H into the optical system, you can see that they experience a shorter and shorter focal length for this particular lens. So that means in this diagram down the bottom that the marginal rays will be focused closer to the lens than the paraxial rays. They'll be focused further away and much closer to the proper image plane, the paraxial image plane, that is. The lateral spherical aberration, you can see that as we change H, the maximum height of rays that can get into the system, that the lateral spherical aberration gets greater and greater. And just to remind you, the lateral spherical aberration is if you go to the focal plane where the image is supposed to be focused and you measure that blurry circle, that is your lateral spherical aberration. And you can see that it increases up to, in this case, up to about 0.4 of a millimeter. So an important way that we can reduce spherical aberration is to close down the aperture stop. Another interesting way that you can reduce spherical aberration is by changing the lens shape. Now you can see in this diagram here, I've got 5 lenses and they all have the same focal length. They've just got slightly different R1s and R2s. However, the amount of spherical aberration is different in each case. Interestingly, in these two situations, the amount of aberration is different. Even though it's the same lens, it's just been turned around. The way that the spherical aberration is minimized is by trying to make the amount that the ray is bent or deviated kind of uniform, so equally distributed, in this case on both sides. So if you look at this example here, a ray that is normally incident won't undergo any refraction at the first surface. It's only at the second surface that all the refraction takes place. Whereas you turn the lens around, then you will already have some refraction taking place at the first surface and then another amount at the second surface. So we've evened up, as it were, the angular bending that takes place. The way that we quantify the shape is using the shape factor, Q, or sometimes sigma, which is simply a function of the two radii of curvature. So how can we get rid of, or at least minimize, our spherical aberration? One thing we can do is not use a spherical lens. We can use an aspheric lens. It's expensive, but in some situations you might want to do that. We can also shut down the aperture. So we will increase the F number, and that will restrict us to paraxial rays. We can also make a compensating diverging lens, add that to our system. And finally, what we can do is we can do something called lens bending. In other words, change the shape of the lens without changing its focal point. And for a certain image and object distance, there is a certain shape factor for that lens that will minimize spherical aberration. This thing here, this pi, is the position factor, and it depends on the image and object distance up here. In this problem, we have a lens with a positive power, so it means that our focal length is positive. It's made from glass with a refractive index of n is equal to 1.5. We are also given our object and image distances. We need to find the lens shape that's going to minimize the spherical aberration. So to do that, we need to find the appropriate shape factor. And to find the appropriate shape factor, well, we know that that's a function of the position factor, so we need to calculate that as well. So we saw that spherical aberration causes a point object to become a bit of a blur, and even if that object is on the optical axis. Coma, on the other hand, only affects light rays coming from an object that's off the optical axis. In this case, we've got an object at a distance of about infinity, and its rays are coming in at an angle of theta with respect to the optical axis. Now, what happens in coma is we sort of see a variation in the magnification with the aperture size. So the rays passing through the edge portions here are imaged at a different height, so they're imaged out here, to those passing through the center. They're imaged up here. Now you can see that that's equivalent to these marginal rays, in this case, having a lower magnification than the paraxial rays. So I could write magnification of the marginal rays here is less than the magnification of the paraxial rays. That's an example of negative coma. Now the distance here is called the tangential coma. Now you might be asking, well, that explains certainly why a image might be sort of elongated, like a line, but why circles? Where do the circles come from? I'll leave it to you to look up the details, but essentially what's happening is if we look at the lens face on, so at the moment in this one we're just looking on the side, but if we look at the front of the lens, then we see that rays that come from here and here are indeed focused at a certain point up here compared to where the on-axis rays are imaged, the tangential rays. Sorry, in this case we're talking about positive coma, just to clarify that. Now what I'll do is I'll change colors and you'll see something interesting. Rays from here and here are actually focused to a point here. Something else more interesting, if we look at rays that come from here and here, they're actually imaged over here. And final color, let's choose purple, why not? Rays going through this part of the lens are imaged over here. So you can imagine that the rays that make up this circle are actually imaged into a circle like this. And then as we go into look at rays that are going through smaller and smaller circles, then they are imaged as smaller and smaller circles that are translated more closely towards the paraxial image. This angle, by the way, is also always 60. So as we mentioned, the coma only affects the off-axis objects, and if you have a point object, then the point image depends on its position. So you can see that in this diagram down here, as we move further and further away from the optical axis, then the object is imaged more and more like a comet. The apex angle, as I mentioned, well, the half angle is 30 degrees. So can we get rid of coma? Yes, of course we can, and in a lot of circumstances we should. So if we look at our little coma diagram like this, where that's our 60-degree apex and there's the Gaussian image point, then this distance here is our tangential coma. And there's a little coma patch down here that's called the sagittal coma. And the sagittal coma is equal to 1/3 of the tangential coma. Right, so we know that this circle here comes from the rays at the outer perimeter. So clearly reducing the diameter of our lens is going to reduce our coma because these circles will disappear. We can also use a different lens shape because it just so happens that the condition for zero coma is close to that for minimum spherical aberration. A really useful word that you can remember is called an aplanatic. So an aplanatic lens or aplanatic system is one that has got rid of coma and spherical aberration. We can reduce it by, of course, using the aperture stop. We can use a lens pairing, and we can also do the lens bending trick, that is playing around with the shape factor in the same way that we did to minimize spherical aberration. I've introduced the terms tangential and sagittal, so I'm going to discuss these terms a bit more now. Normally, we draw our lens systems by drawing the axial section. So that's our lens as seen from the side, the optical axis as seen from the side, and in this case, we've got an object point G, and we have rays coming from that object point and propagating through the system. So this plane, which in the way that I've drawn it here is the plane of the screen that you're looking at, contains the off-axis object and contains the off-axis object here and the optical axis, and this is called the meridional plane or the tangential plane. And these rays, which are located in the plane, are called meridional rays. Now we're dealing not with a two-dimensional but with a three-dimensional system. So not only do we have this meridional plane, you can see that the meridional rays are indicated in pink, but the lens also extends in other directions, and so any other rays that travel not along the meridional plane are called skew rays. So those are the rays that are not in the M plane here. Now the skew rays that are in a plane that is perpendicular to the meridional plane are called sagittal rays. And I can illustrate for you that those sagittal rays actually see something quite different. So now we're looking at the optical system from above. Our point object G is located directly below the optical axis, so it looks like it, from this point anyway, it looks like it's on axis. So we have rays that extend through the optical system like that. If we draw the meridional plane edge on, you'll see that the edge of the plane looks like it's going along like that. Whereas the skew rays, or at least the sagittal rays, look like in this first diagram, then the edge on of that sagittal plane looks like that. The meridional and the sagittal rays see a different focal length, and we'll shortly see why that is. So what does astigmatism do to our image? Astigmatism, you can think of it as like extreme coma. The oblique rays, instead of forming, the bundles forming little cones and passing through a point, they actually pass through a little wedge, and the edge of the wedge forms like a little focal line. So what it means is that it's impossible to make a focused image where the outer parts of the plane object that are perpendicular to the axis like radial details, can be in focus at the same time as tangential detail. If we look at, say, 3 discrete points on our object here, then they will, at one focal distance, be imaged as lines like this. And if we look at, say, these 2 points here, at another focus, they are also imaged as lines. Let's first consider why the rays see a lens having a different focal length, and then we'll see what effect that has on the image. So we'll first of all consider the sagittal plane. So we're looking down from above. And remember that our object point G is like directly below our optical axis, and we're looking from above, so it looks like it's on axis. But let's also put it out to infinity just so that it's easier to draw some nice parallel rays coming in. So here they come. Okay, now to make it just a little bit easier to visualize, I'm going to draw in the wavefronts. And you can see that as far as these wavefronts are concerned, they are interacting with a lens of diameter d. Now, let's look from the side at the meridional rays. There's our optical axis and our lens again. But now, of course, G is below the axis. Let's say it makes an angle phi with the optical axis. And it's at infinity, so we've got parallel rays coming in again. Oop, that's supposed to be parallel. Okay, so now let's draw in those wavefronts again. Okay, and so you can see that as far as the wavefronts are concerned, it's now interacting with a lens that has diameter d prime, and d prime is less than d. In fact, it's going to be shortened by a factor of cos phi. Right, so our lens is shorter, apparently shorter, but it bulges out the same amount. So that's equivalent to saying it looks like the lens actually has a smaller radius of curvature. And having a smaller radius of curvature gives it a smaller focal length, which is the same as saying it has greater power. So the meridional rays see a lens with greater power than before. How does this affect our final image? Well, let's start off with an object that is an array of 3 by 3 point objects. Okay, so here's our object. Now we're going to go and look out at the tangential focus. We'll put our image plane out at the tangential focus. So in other words, where the meridional rays all come into focus. So in our first little system, the previous slide, we had our object point G down here. Okay, so that's going to be imaged up here. The tangential rays or meridional rays are in focus. But the sagittal rays are not in focus yet because they see a longer focal length lens. So that's the plane that looks like that. Okay, now if we look at an object that's above the optical axis, then that's going to be imaged like that. As we rotate G around the place, then you'll find also that the meridional rays plane and the sagittal plane also rotate around. And sagittal rays are still always going to be out of focus. What's more, the further you go out, so these ones that are out on the diagonal are going to be even more out of focus. Now let's go back to even further to the sagittal focus. Okay, so on axis point is still imaged as a point, but the tangential rays have already gone out of focus, so they're diverging again. And in this case, for our object G, that's going to be imaged as a vertical blur now, because those are the out of focus meridional rays. And as we rotate our object around, then you'll see that we have what looks like spokes of a wheel instead of points. Now, if we look halfway in between, then the tangential rays are starting to go a little bit out of focus, and the sagittal rays are starting to come a little bit into focus. And so what ends up happening is you have like little sort of blurry circles like that, which are more blurry the further away you go from the optical axis. And these little circles are called the circles of least confusion. The amount of astigmatism in a lens is a function of lens power and the angle of inclination of the rays, alpha or phi, whichever symbol you prefer. And you can use a diaphragm or a stop to limit the size of the bundle of rays that are going through the lens. If the lens perimeter itself is limiting the size of the ray bundle, then the astigmatism is equal to the image height squared divided by the focal length of that lens. We can also use extra lenses in order to reduce the amount of astigmatism. Let's say you've got rid of all the other aberrations, and so all the rays that hit your lens converge together at one point, not at several different positions. Now we end up with another problem. Unfortunately, the points at which they converge are not on a flat surface. They're on a curved surface. Now this is clearly a problem for things like in a camera where the CCD is flat. It means that if we were to place the sensor here, although objects in the center would be in focus, objects that are far away from the optical axis would be out of focus. We could try and compromise by moving the plane somewhere else, but there's still nowhere where you can put a plane where all point objects are going to be in focus. So let's illustrate our paraxial image plane here and our full curved plane like this. And there's the optical axis there. So this direction up here is y, and the difference in between the two planes, that distance, is delta x. So delta x is proportional to y squared, and it's also proportional to 1 over the refractive index times the focal length for each of the lenses. Sum those all up. So for a two-lens system, then you just substitute in m is equal to 2. If you want to flatten your field, that is, if you want delta x to go to 0, then clearly this term here has to become 0. And so you can play around with your choice of refractive indices and focal lengths in order to flatten your field. And fortunately, you might play around with your lens shape to minimize your spherical aberration and your coma effects. It then unfortunately maximizes the astigmatism and field curvature effects. So when you're designing lenses, it's always going to be a trade-off. We can flatten the field doing a couple of different tricks. One is to use a special lens design called an astigmat. That type of lens both flattens the curvature of field, and it also corrects for astigmatism. The other thing we can do is we can just give up on the idea of flattening the field and we bend the image detector instead. And you can see this example here on the right-hand side. This is the Kepler Space Telescope, and the CCD array is quite curved. So we've got rid of all of our other aberrations, but unfortunately there's still one more monochromatic aberration that'll make our life a misery. We have point-to-point imaging, but unfortunately the image, sharp as it is not the right shape, it's distorted. The amount of distortion is the displacement of the image from the paraxial position. So we can express that as a fraction. This can be the height of the image with distortion. The height of the image with distortion as a fraction of the height of the image. That's the fractional distortion. It turns out that it's proportional to the height of the image squared in the first place. So as I move along in this y direction, the percentage of fractional distortion is going to increase. If this number is greater than 1, we talk about pincushion or positive distortion. If the number is less than 1, we talk about barrel or negative distortion. So we still need to get rid of distortion, particularly in applications like microscopy or medical imaging. You need to measure your distances accurately all over the field of view. So although the point spread function is still a point, we have this variation of magnification. We can reduce it by using a stop, either close as possible to one thin lens or making a symmetrical pair of lenses, and if all else fails, we'll do some post-processing to correct it. So as we discussed, our point spread function of an object point is imaged as a circle, and that will depend on where the image plane is placed. So if we place it in the middle, we'll have yellow rays in the center, red and blue rays on the edge. But as we move that plane forwards and backwards, then we'll see different color variations. Now, in this converging lens, then the focal length of the blue light, as you can see, is going to be less than the focal length of the red light. However, for a negative lens, then the situation's actually opposite. We'll have the focal length of the blue light is actually greater than the focal length of the red light. And so a careful choice of a positive and a negative lens and also their respective refractive indices can be used to make a doublet lens. And an important word to pick up on is it's achromatic. That is, it has now a focal point which doesn't depend, well, as much on wavelength. So what we're going to do is we're going to combine two thin lenses so that we can cause the focal point of red light to overlap with the focal point of the blue light. So the first lens will have radii of curvature R1 and R2. The second lens is in contact with it, so its first radius of curvature R3 is going to be the same as R2, and we have R4 as the final radius of curvature. So for two lenses in contact with each other, the total focal length is given simply by the sum of the inverses of the focal lengths. And so we know, using the lensmaker's expression, how to find the focal length of each of those glasses. We also know that we need to use a similar expression for the focal length of the blue light, which is going to have very different refractive indices. So we've equated our focal lengths for red and blue light, and we've gone through and simplified the system, and we've got a design for our lens. It's convenient to specify the focal length of the compound lens as that associated with yellow light. So it's about halfway between the blue and red extremes. And what we get is a ratio, and the ratio is that of the Abbe numbers. So remember, with Abbe numbers, the lower the Abbe number, the greater the dispersive power. And we know also that Abbe numbers are always positive. So because of this negative sign, it means that one of these focal lengths has to be negative. So we had to have one diverging lens. Now there still is a residual chromatism because, as you can see in situation 2, we've made the achromat and we've managed to eliminate focusing error of the blue light and the red light here, but we still have, for all the other wavelengths in between, quite a considerable focusing error. So you need to go to higher performance lenses, which means 3 or more elements to correctly focus 3 or more wavelengths. But they are expensive, but you may need to use them if you are dealing with imaging at a wide range of wavelengths.